Okay, I think we are live. We've got recording, we've got the computer, we've got the webcam stuff. All right, I think this is good. We are live. All right, brilliant. Let's pause that one there. All right, so, okay, let's have a look. I'm going to get rid of that for now. Okay. Hello and welcome back. In today's stream, we're going to continue where I left off on the last one, which is to do with the micro robot projects I've been working on. If you're new to this video and you just sort of happen to come across it, we are building a micro robot project. I call it micro because the idea is that I'm going to try and get this as small as possible for some very good reasons. One of them being that it should be a lot easier and quicker to print if it's nice and small, assuming we stick to within the requirements or within the specs of the free printer, which I'm hoping to be using for most of this project. On the last video, I made changes to the wheels and how the tracks kind of work with that. I wasn't particularly happy with it because when I was doing the test on the last stream, I found that the actual wheels themselves were, well, at least the dummy wheels on the back. Maybe I should recap a second. So the way that the micro robot works is that there is a, we got two motors, 3-volt motors that are using planetary gears to drive the whole thing. Kind of brings down the speed of the motors a bit lower down to something more manageable. I'm not looking to have a high-speed robot. I'm just looking to have something moderate, something kind of reasonable. We can always play with speeds later on in the future. I did mention in the previous video though that the idea of having kind of a slow motor to start with meant that when we come to do some PWM onto the actual motor, we'll be able to have further control of the slowest speed. If you try to PWM a standard motor without any gearing, there's only so much speed reduction you're going to have, and you will actually end up having to sacrifice some torque because of that. So the idea is that I wanted the motors to have as much torque as possible at the lowest speed, and I also wanted to be able to finally control that speed anyway when it's quite slow. I don't envision this to be a nippy little robot anyway. I wanted something to be kind of nice and slow that it can do precise tasks with. Now, in case you haven't watched the previous video, the idea with this whole project is to try and experiment with some of the higher level concepts for robotics, such as swarm robots or swarm behavior. And I mean, you've probably seen videos on YouTube for things like swarm behaviors on quadcopters, which are pretty good application for that sort of stuff. But I wanted to build something a bit more simpler that can allow us to go straight away into experimenting with the behavior and not having to worry too much about having to try and stabilize a robot or anything like that. So I figured trying to stick to something simple, like a little, a differential driven, essentially a track driven robot, where very little is required to get it to go from A to B. But kind of the whole thing really, it just came down to that it should be cheaper to make something like this than it would be to make something like a quadcopter. For one, there's only 2 motors rather than 4, at least for a quadcopter, I mean. And secondly, printing something like this is fairly easy, and the driving electronics is even easier. There will be some complication with we're trying to work out the positioning of the robots, something like either with Dead Reckoning or trying to have something a bit more absolute than that. But we'll deal with that in the future. For now, I'm going to try and get something that can move on its own, as accurate as possible, as low cost as possible, and ideally as small as possible, because I really do want the name micro robot to be meaningful. Because I mean, although that already is quite a small robot compared to some of the platforms you can buy from somewhere like SparkFun, Adafruit, or anything like that, it's still not quite as small as I reckon I can get it. And what I mean by that is, if you're on the screen, I'm showing you the 3D model of what I've done, of some of the changes that I've made to this robot since I last streamed. And you can see that I already pretty much half the distance between the dummy and the drive wheel. So it should be already quite small, but I reckon I can get it a little bit smaller if I move the motors around a bit. Although to be honest, I kind of think at this point it might be worth just to sticking to what I have now, but I will go through the design anyway and explain what I've done. Anyway, so that's kind of all I've done so far. As I was saying on the last stream, I made some changes to the wheels themselves, the way it was driving the tracks, because the previous design that I had was just 2 smooth wheels, and I just assumed that the rubber property or the rubber band was enough to keep enough tension and enough grip between the 2 wheels to keep them both in sync. The problem is that, well, first of all, there is no driving grooves on those rubber bands themselves, so yeah, if there's any force acting on the rubber band that sort of prevent it from moving, yeah, you're just going to end up getting some slippage. So the idea that I had on the previous stream was to add some grooves on the actual wheels themselves. I mean, I'll show you the design. Actually, I'll show you now, really. I don't know why I shouldn't really. I think, yeah, there we go. There. All right, let's take off the webcam so you can get a full view of the whole thing. So, yeah, I made the changes like this so that you can kind of see there was a little bit of material on the actual wheels themselves to sort of cut into the rubber band themselves and sort of provide a bit more pressure on the rubber band. So essentially you're focusing more of the actual traction into a single point, so it's easier to move the rubber band across. To be honest, the first thing I had an issue with, and you can probably, if you're an experienced user of a 3D printer, you probably already figure this out, but those features are quite small. That we're talking about, I mean, if we take a measurement of that using the eye tool on this Fusion 360, you can see that if I was to measure across, say, the widest point of that feature, it's looking to be about like 0.29 of a millimeter, and that's pushing it already at that size. And when you come to print the smallest point down here, I mean, there's no brainer. Pretty much all of this is going to be, I guess if you think about it this way, when the printer tries to print this part, it's going to end up in a way averaging out the overall feature and essentially kind of smooth it out. So you may have some bumps, but they're going to be quite circular. I mean, which is what I found anyway when I was printing the model in the first place. Essentially, that I've added the grooves, and it might be helping a little, but it wasn't a big help anyway. It wasn't a massive gain on the amount of time I spent on making this. It wasn't enough of a gain. So I wasn't particularly happy with that. So I've decided to move away from that altogether, from using rubber bands. And there were some other reasons as well why I was using the rubber band. I figured, yeah, getting a hold of some rubber bands like this would be quite cheap. You can go anywhere and buy yourself various size or various packs of rubber bands. But what I found in the previous video, that I left the robot with one of the rubber bands on since I first made it, which was almost a year ago. And the rubber band itself, on one side, because it was already on tension the whole time, it loosened up a bit, and it became a little bit brittle. And one of them ended up snapping within that year, and the other one, even though it lasted, it didn't feel like it was as tension as I would have liked it anyway. So I'm certain that there would have been some slippage in there. Which wasn't, to be honest, like, if you're buying a lot of these rubber bands, you can just easily replace them, but I want to make the robot a little bit more robust than just hoping that it will last long enough for a week or two. I mean, it's really bad engineering anyway. If a year's time I come back to a project and power it up and I find that half of the stuff aren't working. So, it'd be nice that once I've made this in, a year or two, 10, or even a lifetime, the robot is in a good enough condition that I can just quickly get it up and running and off it goes. So, that's that I wanted to kind of sort out. And the other thing I mentioned as well is that the way I am keeping the dummy wheel at the back in place, I don't know if I got that, yeah. The way I'm keeping the dummy wheel at the back in place is using a M3 screw, and I'm also using an M3 nut. Let's have a look if I've still got the model somewhere. Should do, yeah, here we go. Let's have a look. Yeah, okay, so I think, so it's kind of hard to tell, but I mean, this is one of the first 3D models that I did for this design, and so the motor is expected to be in the front here, and the dummy wheel is supposed to be placed down here. So got myself some small little motors like this. They're quite cheap in AliExpress, eBay and stuff. They're small little DC motors with planetary gears. I got pictures online of the actual gears or how that's made out. They're really quite interesting. In fact, there are loads of 3D models in Thingiverse for you to experiment with planetary gears if you want to know a bit more about that. But for what I needed, it's more than sufficient. And I know this is a bit of a recap if you already watched the previous video, but these motors run at about 50 RPMs, thereabouts, so they are quite slow, which is good. It's, you know, higher torque, lower speed, and so when I come to step down the speed on these motors, I should get some more. I should still be able to maintain some of that torque, even at a slightly lower speed, for more precision work. So, you know, this is kind of what we want. So saying the issue is that the back here, I was using a a brass insert, which looks like this. Hopefully the model will load. There we go. So I was using this brass insert, which you can buy quite cheaply again from AliExpress, eBay, or anywhere like that. And the idea is that you use a hot iron on one end to push this insert into whatever material you want to use, usually plastic like this, and it essentially gives you metal thread on areas on plastic that you wouldn't necessarily be able to achieve. So essentially, you by getting that metal thread, you're able to use M3 screws or standard M3 screws and reuse those parts. And that's kind of like I wanted. I wanted to be able to 3D print most of that, and then use those metal inserts to provide the thread that I needed, so I didn't have to do any tapping, or worse yet, I didn't want to force the screw into a smaller hole in the plastic and so force a thread through, because that's kind of where that will wear out, especially if you're experimenting, especially if you're planning to use it for this for an experiment. You need to take things apart and put it back together. So I wanted to be a bit more reliable, so that's kind of why I wanted to go for a metal insert. Now, I moved away from using this anyway, and I'll kind of recap the idea in a second of the iterations the changes that I've made since I did my last video. But the point I was making is that because I didn't have these metal inserts at the time, I was just essentially heating up an M3 nut and pushing that through that same hole, which just happened to be good enough to push that through to quickly do some tests. Because the issue is, if you use these metal brass inserts, if you have a look at the design, you've got inverted threads or inverted teeth on them. So once you push the plastic through, so if you imagine that the plastic goes through in this side, you're pushing the inserts in this direction. Once the plastic settles between those gaps, it's really hard to remove this part and reuse it. So rather than trying to waste metal brass, or rather than wasting this insert on my test pieces, I just decided to use some cheap M3 nuts, which, to be honest, you could just use that if you're just experimenting quickly for this sort of stuff anyway. But the end result for me, I wanted to use it, so I wanted to make sure I was still able to use that. But that said, though, I've not wasted any of them, and now that I've made some changes to the design, I don't think I'll be using them anyway. But I still have some issues that I want to try and fix today. The issue is that because I'm using threads, and the screw has to go through the wheel. There we go. Because the screw still has to go, I mean, I know that's not the M3, it's just a standoff, but because the thread still has to go through the hole, either I make the hole wide enough so that the thread doesn't catch on to the wheel, which means that there will be a bit of slack on that wheel itself. I don't know if you can see that. There will be some slack in there, but that's enough to give enough clearance for it to rotate freely. There's going to be two issues with that, is that after the wheels are rotated enough around that thread, it will slowly wear out that inner hole, or the inner hole, which is not great, because it means that wheel will slowly wear out, especially when you've got the threads on there acting on it. So either I replace the screw with one that has a smooth collar and then some thread that it can still grab onto stuff, or I come up with an alternative solution altogether. The thing is, if I just stick to using M3 screws like this, it will wear out the wheel. That's one of the things. Or if I make the hole too small, it won't rotate, or it could grab, which is a bit annoying. And then on top of that, I also want to make sure that the screw stays in place. So if I put any thread sealing or anything like that on the actual screw itself, it could get into the side of the wheel, and it basically makes it very hard to have a consistent working design. So I want to make changes to that. I know this seems like a lot of work just for a single wheel, but this is the sort of stuff we need to think about anyway when we're designing little robots. Because the thing is, we could just whip something out quickly. I mean, I could just call it quits with that and just, yeah, all right, that's a good enough design I could play with. But I want something that is reliable enough for me to experiment with other stuff. I don't want to, I mean, excuse me if I say this, but when I first built my first 3D printer, which was made out of random kit parts that I bought online, I ended up spending more time fixing the printer than actually using it. And in the end, I got fed up and decided, right, I'm just gonna have to buy one that would just work, and hence the new printer that I have here, new, well, 2 years old, which kind of removes the whole trying to fix things and just focusing more on the printing. And I want the robots to be the same, especially because what I want to use them for is to experiment with other robot concepts. And if I'm spending a lot of time having to deal with the mechanics or the reliability of the robot itself, then it kind of wastes the time that I could be spending on trying or proving or coding some new concept or anything like that. So yeah, so I'm spending a lot of work on this, but I feel like this will make a big difference anyway. So today I'm hoping to try and sort out something with the back wheel, the driving wheel, to make sure that it's reliable and it constantly works, and I don't have to worry about when I assemble it to assemble in a particular way. I want it to be a bit more foolproof, so that if, you know, future me in a year's time doesn't stupidly build a robot and forgets to do some random sealing or whatever gluing. So yeah, it's trying to future-proof this for idiot me in the future. So yeah, let's see if we can achieve that anyway. Anyway, so the other thing I did on the previous video is I ordered some H-bridge boards, some little cheap little H-bridge you can buy from Amazon, eBay, all that places. I was quite interested on the chip themselves they were using, because you see the motors that I'm using are 3 volts. They're about, I mean, when I was testing them, they didn't go any more than about 100 milliamps when this was on load as well. I mean, I still need to test that out because I didn't really scope out the current to see what the true peaks were. I was just assuming that whatever my my power supply and multimeter was kind of good enough, or at least a good ballpark figure anyway. So the ICs that are in these look to be more than adequate for driving this motor, and I thought, okay, that's not too bad, let's order that. And it comes with 2, so I'm able to drive 2 of these motors in both directions, so they're, you know, the full H-bridge. The only downside with this, normally when you buy H-bridge chips, you're able to have 2 separate supplies for both the supply that drives the motor and the logic to drive the chips. This particular ones that I bought uses the same supply for both the motor and the chip. Not an issue, because the voltage that's going to be driving the motor is the same as that of the microcontroller, 3.3 volts, which I think is within the limit of this motor. So yeah, I can get away with using the same supply, but the nice thing about having a H-bridge that has 2 separate supplies for both sides, the motor and the driving, the logic side, is that usually you can provide some isolation with that. The chips usually support some isolation, so you're able to, if you wanted to, use things like optocouplers very, very easily on one side without having to worry too much about the other side. Where with this, if I want to isolate the 2, I will literally have to not only put opto-isolators for the IOs, but I also have to do a isolating for the voltage for the 2 sides. And there's a risk as well that because both sides are powered by the same supply, that when one fails, then it could easily mean that it could fail on the other side as well. Where when you have H-bridges with 2 separate supplies, if one side fails, there's a good chance that the other side will survive as well. So you'll be able to do a bit more error checking, not error checking, but you can do a bit more redundancy, fail safes without kind of talking a little bit out of that, really. That's out of my depth because it's not something I usually go into anyway. But alright, so the other issue I found is so in order for me to make this screw and back wheel to work, and I think I got it there. In order to get that to work, I had to use a washer between the actual robot chassis and the wheel itself. Even though I did kind of print a little bit of a washer that already on the actual wheel itself, it wasn't enough. I needed enough gap in order for this to freely rotate. So that was a bit of an issue, and I had to put a lot of sealing, Loctite sealing on that thread itself, on that M3 screw, I mean, to really get this to rotate smoothly. And you see, this is what happens when I didn't put that washer in, and secondly, I put way too much Loctite to get that in place. So the wheel is now, yeah, okay, I can just about move it, but yeah, I can't really expect that that rubber band to actually make it move. And the other thing as well, you can see that if I can easily make that track rotate the back wheel, and you can see that it actually is rotating all around. So the actual grooves that I did on the wheels wasn't good enough, so that needs to change anyway. But it's not the end of the world. I can deal with that. Right. So what I've done so far is, you don't really need to see my webcam. You should be able to see the model a bit better. So what I did is a couple of things. So first is, if I do the section view, there we go. I've already done one already. So what I've done is I got rid of a couple of things. First, I decided to use some, I'm going to regret this, but I bought some stainless steel M3 rods. They're quite cheap. They came in a pack of 10 for about £3, and they were about 320mm each in length, which was pretty good. But the cheapness comes from the fact that it's stainless steel. So it's going to be quite a hard material to work with in the first place. So I'll have to deal with that soon enough, cutting wise. I mean, I think I've got the right cutting disc for my dreadmill, so that should help. If not, I'll have to buy a hacksaw to do it manually, but I don't think it's the end of the day. So the idea that I had is that I was going to have a single axle on the back, then I was going to create matching holes in the actual wheel themselves so they can freely rotate on that axle. And the thing I was thinking about trying to get it to, the thing I was trying to think that would allow me to make this a little easier to work with, so I don't have to worry too much about locking in the wheel. Essentially what I'm trying to say is the thing I was trying to figure out at the time when I did this was a way to keep the wheel in place with a single axle. I figured, well, stainless steel, you can buy them so that they're magnetic, so they are attracted by magnets. And so I thought, what if I get a couple of magnets like this? I mean, I think I'd be able to show inside. What if I cut a groove? If I do like an insert groove on the actual wheel itself, I can insert a magnet on one side, and on the other side is the stainless steel rod itself. So the magnetic force is what's keeping the wheel in place against the axle. And I was playing around with that idea, and I thought, actually, that's not a bad thing. Let's give that a go. And so I had some of these stainless steel rods laying around, and I happened to have the magnets from a few years back from an experiment I was doing. And I thought, okay, let's give that a go. And I made this design, and I figured, okay, I'll settle with this length for the axle rod, and I'll stick to this dimension for the wheel and everything else. And then I realized there's one thing I ought to check, and that is that the axles, the stainless steel that I have, is truly the magnetic one, because you see, I bought a cheap one from Amazon, and it didn't really specify the alloys that it used. So I came to put the magnet on the axle itself, and lo and behold, I got the cheaper one, the one that's non-magnetic. So this design is not going to work unless I decide to buy the axles, the stainless steel, well, at least the version that will be magnetic. And then that got me thinking that actually, if I had that issue of buying those cheap rods without being able to, without it being obvious that this is going to be the magnetic one, how much of an effort is it going to be if somebody else tries to replicate this robot? So I'm going to move away from this design. I'm still going to use the metal axle, the stainless steel rods, but I'm just going to get rid of the magnets as the means of keeping it in place. What I'm going to do instead, I'm thinking what I might do is I'll extend the axles out. Probably should check if anybody's logged into Gitter actually. I haven't really checked. Let's have a look. No, nobody's logged in. Okay, that's not an issue. Let's have a look at that. Just gonna quickly log in just to make sure I've not forgotten anything about that. Okay, that will do. So, I was saying, so what I'm going to do is I'm going to extend the stainless steel rod so that it pokes through both dummy wheels, and then I might just 3D print a little cap at the end that will keep the wheel in place. I'm thinking that might be a good solution for that. I'm not 100% certain, to be honest, because the thing is, the caps, there needs to be something that will keep the cap in place anyway, and I was playing with the idea that maybe if I 3D print a little cap that kind of attaches at the end of the rod, will be pressure fit. It will pressure fit in place, and that seemed okay. I think the issue is that after a while that cap will wear out, so it's not going to be that reliable. So I'm thinking what I might have to do instead is, and I think this might be the better option, is if I make the rods slightly longer so they stick out to, say, where the end of these magnets here, there and there are. If I can make it stand out to that far, then what I can do is I can cut a little key slot on the rods themselves, like a little groove, and then that way when the caps go in, they'll have like a little lip inside that it will use to clip into the actual rod itself. So I mean, I'll try and do the model today to be a bit more precise about that, or to be more specific about that. But if I do cut a groove on the side, on like on both sides of those on that rod, it should give me a little bit more option of putting clips in there. Now, although that said, I do know you can buy, so I do know you can buy little metal clips anyway for this sort of application to keep things in place. But yeah, I didn't want to rely too much on mechanical parts, or at least on the vitamin parts of the design. I wanted to try and stick to doing as much of it 3D printed than anything else. So that said, let me get rid of the section view. The drive wheel is being held in place purely by friction. Let's get the webcam back up again. There we go. So yeah, the drive wheel here at the front is being held in place purely by friction, and it's doing a pretty good job in staying in place. I mean, I do find it very difficult taking that out. So part of me thinks that a pressure fit push cap against the back wheel might be more than good enough for what we want to do anyway. So I mean, the way that would work is that if I designed the whole of the dummy wheel, say at the back, to be exactly 3 mil, or exactly to be 3 mil diameter, so that it matches the rod itself. So when you push the rod into the wheel, hopefully, because the 3D printer tolerances should kick in, so that it should allow it to have a little bit more of a snug push in there. I mean, it can work. It's a double edged sword. It can work both ways. So I think if I stick to, so you know what? If I stick to this, I think that might be the better way to do it. So if I design the cap so that the hole inside where the rod will go in is 3 millimeter, and I know with my printer that's going to be smaller, about 0.1 of a difference. You know, printer vibrations, tolerance of the actual manufacturing itself, you know, plastic warping and all that, should shrink the hole a little bit. So I may actually have to make the hole a little bit bigger so that it's tight, but it's not too tight, if that makes sense. Yeah, you know what? I think I'll do that because I mean, I'm looking at the drive wheel itself. I mean, that's pretty difficult to push apart. I mean, it will. Okay, the motor comes off before the drive wheel itself, so that's a good sign. Do I have? Okay, here we go. Let's have a look. There we go. So I've got a spare one here that I printed already. There. Hopefully that should be easier to see. Can the camera see that if I do that? No. Okay, that's good enough. Anyway, so if I push that through across like that, I mean, it's in place and it's quite a tight fit anyway. I really have to, yeah, you can hear the click anyway of it coming off. So, you know, there's quite a bit of pressure in there. I mean, you should be able to hear it putting the microphone there. Yeah, there we go. So, yeah, I'll do that. I'll do that. So if I use the 3 millimeter rod, make the hole in the actual drive wheel itself wide enough so that the axle just kind of glides, so the wheel is able to freely move on the axle itself. And then if I cut enough of the axle, if I extend it out, say, let's have a look. Where's my? if I extend it out to, yeah, audio's still working good. Just dropped the, yeah, my audio recorder. So if you see that height of the head of the M3 screw is about, okay, 2.6 millimeters. So if I make that maybe 5 millimeters, that should be enough material on both sides to, I mean, that's actually a bit too much, isn't it? Don't think you can see that from there anyway. Yeah, it's a little bit too far. I mean, I may have to play with that. Actually, I don't think I need that much material. If I make it so that the axle protrudes 3 millimeters out of the top, out of the wheel itself. So from the wheel surface here, the outer external surface, I mean, if I can get the rod to protrude another 3 mil, so that's going to be 6 mil longer than the two wheels and the chassis. If I make that happen, then the cap, I can design that to be, it doesn't even have to be a cap, it can just be a disc that you can push in. That's maybe 2 millimeters. I mean, 2 millimeters is quite small, so we may have an issue when we push that through to the axle rod that it might snap. I'm not certain. I mean, what's this, the wheel width? See, the drive wheel is currently at 3.4. Actually, this is the old design. The new design, which I haven't explained yet, just move this out of the way. If I do, yeah, from here to here, that is looking to be 3.2 millimeters. I don't think you can see the measurement screen on this. I think you can't see that now. Yeah, the screen capture is not showing you that, but it's all right. So 3.2 millimeter wide. Can you even see that there? Yeah, it's just about there. So it's 3.2 millimeters. So if I make the disc that go over the wheel itself 2 millimeters, then that might be enough to keep it in place. And in fact, if we match it the diameter of that wheel, yeah, if we match it the diameter of that wheel there, it should be enough of a surface to keep the wheel in place. So I think I might just do that. Okay, I'm happy with that. So fine. So to recap, what I'm gonna do is I am going to get rid of this magnets because that is a silly idea. Although I would have loved for that to, if the rods that I had were magnetic, I would have loved to pursue that idea because it would have been quite a cool idea of being able to put the wheels in, keep kept in place with the magnet, and then whenever I want to do some repairs or changes to the board, I could just clip them out. Where now I'm going to be relying on a pressure fit clip. I've got a feeling that when I come to remove that clip, it will likely break or wear out quickly. So I may have to keep reprinting some of those clips whenever I want to do work on this. But if it's a printable part, I'm not sad by that. If it's something that I have to buy in, then yeah, at that point I would have probably changed the design anyway. Okay, so. Right, so while I'm here, I might as well tell you what I'm doing now to overcome some of the issues with my previous design. So previously I was going to be using the rubber band. If we get time today, we're probably going to do some more tests with that rubber band anyway, until I get the proper stuff, the belt that I bought, which I'll explain more about in a second, which I think have just arrived because I just heard the door. Well, I just heard the front door, so I think the mailman might have delivered that already. So what I want to do is get away from using the rubber band and instead use belts. So similar to what your 3D printer, if you've got a 3D printer, uses to drive the extruder head and all the other mechanical moving parts around. And the nice thing is with the belts that you can buy them to size. So you don't necessarily have to stick to the standard belt width that most well, like the 3D printer uses, which I think is like 6mm or something like that. I forget on top of my head. You can buy them to the width that you want. You do have to stick to using particular length, but that's not the end of the day anyway. I can quickly show you the site that I went to buy the belts that I wanted. But the key thing is that there's a standard to the pitch of the width of the teeth themselves. It might be easier if I show you the website itself so you can actually see what I mean. Let's have a look. Can I get this up and running on the computer here? I think I might be able to, so do bear with me a second. And let's have a look. Can I? Yeah, the setup that I have here is a bit strange. So I've got my main computer running Windows, doing the capturing and recording. Last time I had that set up, but the graphics card was well underpowered. It had no encoding built in, so it was my 8-core processor doing all the encoding, and yeah, it wasn't the easiest thing to deal with, really. Let's have a look. Can I? No, this is not. This is proving to be a little bit difficult, but anyway, there we go. So if I now go to the webcam, it should be this computer, which it is. That's good. Okay, here we go. So the site that I use is Built-in Online. I think it's a UK company. Yeah, here we go. So this is the company I bought the belts from. I'm gonna be honest, I don't know what they're like. I don't know the quality. I don't know what to expect from it. Let's have a look. I don't know what to expect from their products. I'm just trying them out because the thing is, previously, whenever I needed to buy belts, I either went to AliExpress or eBay. Last time it was actually RS because of a project I'm working with a friend, which I might talk about in a bit. And the issue is that they have to sell the standard belts. There'll be a standard width, there'll be a standard length, and the number of teeth that are in it will be standard. And they're quite pricey. And considering that I didn't want a super expensive belt, which the things, the application for some of these belts are for things like timing, synchronizing, and say like with a 3D printer, creating motion. So in some of those applications, they need to be quite reliable, and so the standard belts that are sold usually have a lot of this stuff to take that into account. So things like they have like fiber mesh inside the actual belt itself to provide more strength, so that there is no, so they don't stretch with time. So like with the rubber band that I have here for the robot, as I mentioned, a year went by and they became quite slack. You wouldn't get that on the timing belt ones or in just belts in general, if they've been designed correctly, I should say. There'll be quite low warping on the material itself, and a lot of that is due to the material that they actually embedded inside the actual plastic itself on the belt itself. Like I said, some of them use not carbon fiber. They use, I mean, it'll say here on the website, some sort of fiber in there. Maybe glass fiber, I don't know. Some of them will actually use steel depending on the thickness. Anyway, the nice thing is that I'm able to buy the belts quite cheaply from this website because they'll cut it to width. And what I mean by that is if I go to their to the one that I went to, so if I go into rubber timing belts, let's go for the inch pinch. Yeah, that's the one. The MXL, that's the one. So this is the one that I ordered, which should hopefully arrive today. I'll probably have to talk about it. Well, I'll probably talk about it, sorry, on the next live stream, because I don't think I'm gonna have enough time to go and get it and play with it today. So the way that they work is that you can, I mean, there's already, for these timing belts, there's already a standard on length and the number of teeth, and also the pitch that is at. So you can choose the length for the rubber band or the timing belt you want to use. And then once you've done that, you can just basically specify the width that you want. And so what actually happened, I think this is the clever thing. If I go into the, there we go. So here's a good picture. You can see they already extrude this the belts into long sections. So like this, this would be pushed through an extruder that will create the correct number of teeth, the correct profile for that, and the correct length. And they'll just basically come out as a long, similar to what you expect in a treadmill, so that long belt sort of setup. And so what they do is they'll just cut into, they'll just slice the length, the width that you want. So as far as they're concerned, you can specify any width for the track or for the belt that you want. If you stick to the standard width, then they'll already have a lot of that already pre-cut and it'll be a little cheaper. But with this company, if you imagine now they'll be able to cut it into sections. With this company, the pricing on this doesn't seem to make that much of a difference if you use the standard width or not. So for example, here, the one that I've ordered, the standard width is 3.18 millimeter, 4.76, 6.35, and so on. Yeah, if you're used to inches, you can probably get the idea behind this particular belt. But yeah, but I don't care to use 3.18 millimeters or anything like that. This is for a very simple application. So I figured out what's the width that I want. I want it in 2 millimeters. Why is that not working? There we go. 2 millimeters, and the smallest length that I can get away with, which was in this case 91.44. The material they use inside to create that strength to the, you can have a look at the picture here, that material that's inside the actual rubber itself, it's glass fiber, and the material of the rubber itself is neoprene black rubber, so it should be quite grippy. And if you calculate the price, it's very cheap. You're looking at like 0.35 pounds per single rubber timing belt, I should say. So I was quite happy with that. Previously, when I wanted to buy timing belts, I had to stick to buying the ones that are offered by RS, AliExpress, anything like that, which were, they don't sell it by whatever width you want to, and they only have a limited range. Obviously, this website focuses on selling just timing belt sort of stuff or related products. So they're able, I'm guessing they're already invested on the money on the cutting tool that they need to be able to cut the right length for all or the right width for all this. So yeah, I think it's pretty good. I've ordered 4 sets of the 2 millimeters, and then also I saw that they had this other type, which was HTD. I'm not sure what that is. I'll probably tell you in a second. Let's have a look. What's HDT? I am not really sure. I'm guessing it's registered, so I'm guessing that's a brand. 3 millimeters. That's a bit deceiving there, isn't it? Because you can still specify the width you want. Anyway, all right, 3 millimeters the pitch. Sorry, yeah. So that's the pitch, that's the profile. So the HDT will be the type of teething or the type of profile teeth that they're using when it's registered and all that sort of stuff. So again, with this one, I ordered 4 of this as well, but the smallest I can do it was 105 millimeters. So I ordered 2 millimeter width. Again, and it's like, okay, a little bit more expensive, but that's not that far off, considering that if I wanted to buy the one I was working on a previous project with a colleague of mine, I went with polyurethane shrink flex. I think it's the T series I did. 2.5 pitch, which is the same pitch as the timing belts you use for a 3D printer. And the one we ended up using for the project we were doing is 230 millimeter length, and it was 6 millimeter width. And this came out like £3, was it? £3.79 for this exact belt, this exact spec from RS. It was nearly £5, and that was excluding VAT as well. With this one, £3.79 excluding VAT. It's not going to go any more than, say, well, it's going to be no more than 20%, because in the UK tax is 20% anyway. And even then, it's nowhere near £5. So it's insane. Like, I'm not going to pay for extra. And on top of that, we ended up using that belt because that's what RS offered. That's what we could get. We didn't realize we can buy exactly any size we wanted to. So yeah, if I had wanted it as 2 millimeter width, it would be about £26. Yeah, £26. So even cheaper, and it will be more closer to the kind of robot projects that we're working on and that sort of stuff. So if you're going to do anything with tracks, reconsider buying your own tracks. You don't have to be stuck buying the pre-standard stuff anyway. So this is a pretty good place to go to. So I bought a lot of these, and they're not too bad. I went for the rubber because I'm using the tracks to drive the vehicle, and I wanted more grip. I believe the polyurethane, I'm not sure if I'm pronouncing that correctly, it's quite slippery. But I needed to buy the exact same one that my friend bought for his project, so they both had the same spec. But at least I managed to save a little bit of money by using this website anyway. But for this robot, I've ordered 2mm by 91.4. Am I on the right one? 91.44mm length. And so what that meant is, if I change now the screen back to the main machine. So what that meant is that I had to redesign the diameter of the wheels. I couldn't use the original one, which is the one I was just showing you here. I couldn't use this exact same one. For one, this was more for the rubber band, and secondly, it's a little bit too small. Because you see, I mean, I probably should get the Google Docs app to show you the calculations that I had to work out, because the thing is, when the timing belt, when they spec the length, that's the overall circumference length of the belt, going all around, well, the circumference is all around, of course, which brings up a good point. But because I'm trying to design it so that you have two wheels, so that you have two small circles, and then the extra length that's left is shared between the two by displacing the two wheels together, just like I've done here. I needed to work out the right diameter for the wheels that I needed, that still had enough teeth in there, it still had the correct teeth profiles to be able to drive the wheels. So if I bring the section view back to, is this right? If I now change it to, let's edit that, shall we? Where did the screen thing go? I'm not really sure why I can't change the section view. I may just have to delete that. There we go, fine. Inspect, section, analyze. Let's do the wheel there. If we just cut into that, just there we go. So yeah, so what I had to do is I had to match the profile of that. Actually, do I still have that here? I think I still do. Would probably, this is going to be a little bit more confusing than it needs to be, but if I go back to the HDMI, yeah, that'll do. So I had to match the profile of the actual teeth itself. Annoyingly, this website, if I click on that picture, it takes me to the wrong belt profile. Let's just get the screen looking at that again. Yeah, the screen is just flashing away. Oop. Yeah, so annoyingly, if I click on that picture, it brings up the wrong profile for the belt itself. So I had to actually look at the picture that is displaying in there and look at it from there. So it's a little bit annoying, but it was fine. So yeah, this is the correct profile for the belt that I bought. So the pitch is a bit awkward. It's 2.03 millimeters rather than a standard 2 mil and from that. But this belt that I bought is for the inch. It's all spec in inch because it's probably going to be for the USA market, or at least any industry that uses inches rather than millimeters. So I could have gone and bought the other belt, the HDT, that looked like this, that looked more like this. But the issue is that I wanted the pitch to be a bit smaller, and on top of that, the track itself is a lot bigger, a lot thicker. So the other one that I was looking at, which is the HTD, I mean the overall thickness is already, the overall depth I should say is 2.4 millimeters, where with this one it's 1 point something, so it's almost half the actual thickness. So again, sticking more true to the actual overall miniaturizing of the robot itself. So I have to kind of plan that thread out. If I go back to Fusion 360, let's get that up and running again. So yeah, with this one, I had to match that. I had to. It took quite a bit. I had to go back into the. I had to go back and get the equations for designing gears to figure out what the right circumference I need for, or the right diameter for both the reference of the gear as well as the root and so on. It's all this annoying gear terminology that I'm trying to make sure that I remember, because I'm sure I'm going to be doing more of this in the future. But again, just put it all through a calculator, all through a Google Calc sheet, and it's going to be there for future anyway. So I may have to go through that. I mean, if people are interested, I'll do a video on calculating the right diameter for the wheels and the number of teeth that you need. And the thing is, I had to create the equation so that it also took into account the distance that I wanted the two gears, wheels, but the two gears to be apart, because the overall diameter of the belt that I bought was 91.44 millimeters, which meant that whatever, if you calculate the circumference of one of the gears, which is essentially one of the wheels, which essentially if you divide it by 2, one for the back, one for the front, because you're only going to have half the belt touching each wheel anyway at any one time, the rest of the length has to go between them. It has to go on the top there, going across there, and the bottom and go down there. So the calculation had to both work out how much of the belt is going to be used up by the wheel, and then what's left over will be the divided by 2 will be the distance those two gears have to be apart enough for the belt to be in tension, or at least in full in full tension. The only concern that I have is that I've designed this to be just to work for that length. I'm concerned that I may have to adjust the length of the two wheels so that it's a little bit more tight on the belt itself. Anyway, that said, once you put the belt on this, there should be about 0.5 of a millimeter left above the actual wheel itself, which will be the belt, which will be what's left over for the belt. But I won't bother printing this just yet, again, because the belts, I think they just arrived today, but I'll do that on the next video. So on the next video, I will get these gears printed, test the belt out, and then see how that works. But for today's video, I'm mostly going to be focusing on, can we get rid of this? For today's video, I'm going to be focusing on redesigning the back so that it uses a single axle that protrudes 3 millimeters on both ends, and design a clip that goes onto that, which shouldn't be too difficult, but we'll see how that goes. Yeah, let's have a look. How long have I been recording for? 51 minutes, it's not too bad. And we still got half an hour before lunch, so can we do this in half an hour? I think we might be able to. Shouldn't be too difficult, I think. Yeah, so again, I'm going to change the length of the rod so it protrudes across, update the dummy wheels at the back so that there's enough, so it lets the rod across, and then design a disc. And then, yeah, I mean, it's a shame because that doesn't seem like a lot of work for today, but it will have to do anyway. Alright, so where do we go from here? We won't need that, and the old drive wheel we don't need, so we'll need which is red. So you're probably wondering, why are the different parts all different colors? I'll be honest, I like coloring up the robot, it's kind of cool, but a side effect is I care more about what it looks like this as a plain solid color and with a bit of shade. I didn't really take into account what the online renderer is going to do once the model has been pushed through to the Fusion 360 cloud, and that is it's actually going to render the surface material each of the models. And the thing is, I chose gold for these wheels, the front wheels, and whenever I get the render, it just looks like I pimped out the robot, which that was far from what I was going to do. I do have gold lacquer, which I used for when I made this metal, 3D printed metal, a few years ago, I say. So I'm actually very tempted that once I get these wheels printed, call them gears because they are essentially gears, they're belt driving gears. I'm tempted to go spray paint the wheels just to pimp it out a bit, but it's more of a joke than anything else. I'm not the kind of person to pimp things out. It was purely by mistake. But anyway, the original point is, the reason I color them in different colors is because on the browser I've made this many different wheels, different variations of the wheels, that I keep opening the wrong one whenever I clicked on the menu here, so I figured it would be a little easier to go to it if I just change the color so I can quickly visualize them here. Yeah, I did the same thing with the chassis because I had quite a few different versions going on there. So yeah, so that's the idea behind it. I mean, really I should just delete the old ones, but I've not had the heart to do that yet. Actually, I say that, I've tried deleting it, but I tried deleting a few of them, but I keep getting messages saying that, oh, it's being used by a different version. I'm not sure why, because nothing else is using it, even the older. I kind of think it may be to do with the history of the model, but anyway, I'm sidetracking. So I'm updating the back ones. So first of all, let's get rid of those magnets, because that was a terrible idea. Well, it was a wishful idea, and I'm not going to use that. Incidentally, if you've got an assembly of this, you can just right click and open the model. I think you could just do it from here. You can just go straight to it like that. So could have just done that rather than just trying to go to the menu here. So, oh well. Now the one thing I'm finding a bit annoying is that there are certain menus that aren't appearing. Like right here, I'm right clicking and there's a lot of menus that have just popped up, but for some odd reason it's not being rendered, or it's not being captured by the graphics card. Possibly it's not being captured anyway, so it's a little bit annoying because it's hard for you to see what I'm right clicking or not. But oh well, at least you can see the overall model, and hopefully if I explain what I'm doing in enough detail, it may not be necessarily a problem, but we'll see. So I'm going to get rid of that groove I did for the magnet, which looks like it's these two history features there. If I remove them, if I go back, it should just get rid of it. Nope. Oh, I see. It's right. I see. It's this there. There we go. Which goes back to the original I had there. And what is that diameter? If I go into inspect, measure. I really don't know why. Does that pop up at all? No, it doesn't, does it? No, it doesn't pop up. Anyway. So the diameter of that is 3.4 millimeters, which if the rod is 3 millimeters, 3.4 is quite loose, that, isn't it? I think my 3D printer has about 0.1 of a millimeter error. If I print it at fast speed, it might be greater than that. So I may actually leave that as it is and play with that. If it's a bit too much slack in the rod, I may decrease it a bit, but we should be able to measure that. So I think 3.4 millimeter in the inner axle for this should be sufficient, I think. There's another thing I noticed that may be a problem for us. If I do another section view of that there, and just, no, that's not going to work. Let's do it the other way, shall we? If I do it, yeah, that would do. But yeah, that's it. Another problem I noticed while I was explaining the project is that I made some washers here. You can see I made it's a bit of a superficial washer really. It's built into the plastic, and that size of a washer sort of groove that protruding feature was meant to kind of provide a bit of rotation and motion, a little bit of a gap, and it's supposed to kind of allow the model to rotate against that without having an effect on the axle in the middle. Yeah, I'm thinking, as you can see here, I did some chamfers on the hull itself to make the insertion of the rod easier. Oh, actually there's a couple of issues here. I'll check in a second. So I want to keep the chamfer because that will make inserting the rod way easier. But that means that I want to increase this this embedded washer to maybe, I mean, I know that's 5 millimeter across there because I remember measuring that before. But if I say add another 2 mil, so it's down here and down here, so like 1 mil radius or 2 mil diameter, then that should be enough material for it not to rub directly on the actual robot itself. The thing is, you don't want to put too much surface area there, because if you do, you are essentially creating a friction disc. So that's, you know, it's pros and cons. So yeah, I'll increase it by another 2 mil. So maybe it comes out down here, and that way there's not too much surface to surface friction between the chassis and the wheel itself. But there's just enough to provide that gap and enough for it to kind of freely rotate. So I mean, that was kind of the idea behind that. I mean, I could reduce the chamfer, but I do think I'm going to be needing that when I'm trying to push the axle rod through. And it also helps to, if you want to do any pre-drilling or use any like deburrers to clean inside. Okay, so I'll increase that by another 2 mil. And I need to fix the hole in the chassis itself, because I'm pretty certain the rod itself is 3 mil, and I don't think the hole the guiding hole inside is 3 mil. Saying that, it looks like it's out. Anyway, we'll see anyway. Right. So let's get rid of these old features I don't need anymore. So just right click and delete. There we go. And then if I click on that, it should highlight the feature this was created. So it's this drawing here. So let's edit that. And so, okay, so it's 5 mil like I said. I want to add another 2 mil diameter. So it should be 1 mil on both sides. Oh, that should be 7, not 5. So it should add another mil there and there. Is that good enough though? I'm not really sure. I mean, it will be. I mean, if I get the measuring tool out and say, I just want to measure this point right. Yeah, no, okay, it's not going to work there. Let's just get the chassis app, and then that should tell us anyway. That would do. And that would tell us what the actual diameter of the outer bit of that chamfer is. So I for the measuring tool, click on the outer one, and the diameter is 4.9. Okay, which makes sense, because if you look at that, there's like 0.1 of a millimeter difference, just about that. So yeah, another 2 mil diameters, which is 1 mil, means it'll be down here somewhere, and that should be more than enough to keep it from going into the chamfer. Okay, I'm happy with that. Stop sketch, and that should update, which it has. And then I left the hole inside a 3.4, which is this one. Is it? Hang on. Which is this one here. So 3.4. I'm not sure if that's a bit too much. I mean, okay, like I said, we'll leave it, we'll print it, we'll test it. This piece should only take no more than 10 minutes to print anyway, and that's a medium size quality, which is I think 0.2 millimeter layer height on the Robox printer. And I think I'm happy with that. I'm gonna leave that as it is. Let's save that and update this here. I mean, you can't see it, but there's like a tree on the left that tells me that it's out of date, and you can see the little warning sign up there. Let's have a look. Can we right click and update all from there? It's taking a while to load. And yeah, there we go. It's updated. That was nice. I could have just right clicked on the parts. I mean, you can't see, but there's like a little tree, a browsing tree that's popped on the left here. That could have just right clicked the individual ones. Now, yeah, oh right, okay, so that's expected. You can see there's like 0.2, 0.4 of a millimeter diameter too big. And I'm a little worried that it might be too much, but I'm sure that the printer tolerances are bad enough that this will be fine. Okay. So that's that. So now what we want to do is create the clip disc that will hold on to the axle rod and stop the wheel from moving back and forth. So we'll need to create a new part, like so. Let's get rid of the gear. We don't need to make changes to that just yet. And if we create a new sketch and then create a circle, like so, from the middle. Now, I said I was going to make it, the thing is, I don't want to make it too big, thinking about it, because as I was saying a second ago about the little feature that I created there to create a bit of a washer effect, if I create too much surface for the wheel to rub against it, you will essentially be adding that friction to the driving wheel itself, and it will wear out if you're not careful. So you don't want to make it too big, but I also don't want to make it too small. So I'm thinking, if the axle is 3mm, if I make the pushing disc or the pushing clip, if I make it, say, make it 5mm, that gives me 2mm working surface, and it only means that only about 2mm worth of the surface is actually acting against the wheel. So if I make that 5mm, the only concern I have is that this disc might be a bit too weak, so we might need to make it thick, quite thick, to make sure that it's enough structure there. And also because it's quite small when you print it, you may want to print quite a few of them in one go, because if the printer is having to print this disc all on its own, some printers, if they're not tuned correctly, I can tell you this is an issue with the Robux. The settings doesn't tend to adhere to letting the plastic cool down long enough before applying the next layer, and it ends up being a bit of a crappy finish, really. So I would definitely recommend printing quite a few of these, or if you're going to only print a few of them, space them out so the head has to work its way hard to try and get to them, and should give it more enough time to cool. So 5mm, and I'm going to do the inner diameter hole by clicking C to create a circle and make that 3mm. And so the inside should be a push fit. You see, I'm concerned I might have to up this to 3.1. It may need to have some space. Oh, you know what? 3 is going to be too precise. Let's go for 3.1, and then hopefully the tolerance of the printer would work with us on this. We'll see. I'm a little bit skeptical with that by now, but yeah, oh well. Okay, so 3mm by 5mm, and if we extrude that out to, again, you can't see the window, which is really, really annoying. If we set the objects, the extrusion to, say, 3mm, yeah, let's have a look. So we said we're going to let this rod be 3mm, and then yeah, we'll do that. Now, I was tempted to create a hole so that it doesn't go all the way through. I was tempted to do that, but that might be a bad idea. You see, if you try to push a rod that's press fit into a tube where there's no air or no way for the air inside that's been trapped to escape, that pressure may actually act against you and force you not to push it all the way in. So because you're essentially compressing that air, but also the other way around as well. Once you've done it, and if any air has had a chance to escape, it's going to create a vacuum. So if you want to try and get the clip back out, it will be quite hard. So at least this way, the air has a place for it to escape, and you should be able to pull it back out again once you're done with it. Now, I'm tempted to add some nice little looking features to this to make it look kind of cool, but yeah, we'll leave it for now. All right, so let's rod, let's just call it clip. And if we copy that name and make sure you change it, you can't see here, but the tree that's on the right hand side, you can rename each of the bodies. I need to look into why I can't rename this, why it's not being displayed. But you can just about see some text appear magically floating. Brilliant. And the reason why I'm naming this is when you export this model as STL, it uses the body name for the export name rather than the file name, which is a bit annoying, but it's not an issue. It's not the end of the world anyway. All right, so we've done that, and now I want to change the color of this because I'm pretty certain this is going to look hard to spot among all the other grey stuff. So I've chosen red. Let's go for something. Let's go with white. Actually, would black be better? Let's have a look. Because you see, that silver and black looks really nice on the motor. If I just show you. Get rid of the body. There we go. See, the silver and black looks really nice. So I might change the wheel to silver and the clip black. No, no, we'll just leave it red. It's fine. We'll just change this one to black. It'll be fine. Wait, I'm thinking about this way too much. What is that? That's still. And that look no different. Let's go for something. Is there a reason why that's not working? Do I need to just put it there? That's weird. Ah, is it just certain ones? Yeah, that's weird. Anyway, let's not lose too much sleep on that. Okay, so the other thing I want to do is update that rod, and I want to, let's have a look. What's the distance between this wheel and that wheel? According to my measurements, the distance is 49 millimeters. So if I add 6 millimeters, it's because 3 on each, 49 plus 3 more millimeters on both sides, I'd say. Does that make sense? 6, it will be 6. So that makes it 55 millimeters. So if I add another 55 millimeters to that rod, all right, and if I right click on that and edit the feature, so if I make that 55 millimeters, then save that. If we go back to here, that should now protrude 3 millimeters on both sides. I hope. There we go. And if now, let's get rid of that section view, we don't need that anymore. If now I add that clip into the drawing, which is, may need to change the color black because I'm getting confused with that one anyway. Clip. Let's put it there. Click OK. And again. And then click OK. Right, so if we do joints, so click J, and then we can click on that, and then line it up to that. That would do. And we'll do a section view in a second to see that there is no interface in between. Well, there's no, yeah, that there's no interfacing. Is that the right? Yeah. No, that's not the right term, I don't think. Just to make sure that those two aren't colliding. I mean, I know that designing this to be precisely 3 millimeters and exactly fit there 3 millimeters is very bad when it comes to engineering, because you really need to think about tolerances when you print this and all that if you want to manufacture this. But I reckon that, well, I don't really care if it fits in. When I push this in, I'm actually going to try and leave a little bit of a gap so it doesn't go all the way in at 3 millimeters. So I may push this in and leave maybe 0.1 millimeter, or maybe a business card's worth of distance between the wheel and the clip itself. It's just there to reduce too much of the slack and still allow the wheel to freely rotate on that axle. And let's flip that around. There we go. And that is it. That should be enough. I mean, right now it looks like there's a gap all around it, and I expect that, but I suspect that once I print this, that gap will be just fine. One more thing I need to do, and that is I need to add chamfer at least on one of the sides, so it makes it easier to push the rod in. So if I modify, add a chamfer, and I choose this side, and I change again, you can't see because the window's hidden, I really need to sort this out, 1 millimeter chamfer. Can we even see that? Why is that now? That's not right. 2 millimeters. The chamber could not be created at the requested size. Try adjusting the size, selecting. Okay, so I'm guessing that 1 millimeter is going to eat up that chamber. So let's try 0.5. All right, that's better. Okay, so let's leave that as 0.5. And what that means is that when we push the rod in for this direction, so like so, when it goes in like that, we'll have some chamfer that will help guide the rod into the center. And then I'm guessing we're going to use a thumb and push it down from this side, and hopefully not cut itself because those axles are a little bit sharp on the end. So I need to make sure I sharpen those. That's just me reminding myself, and let's have a look. I bet I have to rotate those clips. Come on, let go. Hey, what's going on here? That was weird. Alright, so let's update that. Hopefully it's not too bad. Alright. And yep, this one needs to be flipped because it's the wrong side. And they both need to be flipped. Alright. Alright, let's start with the first one then. Let's edit that joint. And let's think it was this one. I need to do this side, I think. And has that going in the right way? Ooh. Yeah. Alright, and let's do the second one. Edit this one here. There we go, that's done it right. Okay. Yeah. Now we need to look at the section view again, because there's a couple of things we need to fix. You see the chamfer there, that should hopefully help it push it in. And yeah, we got about, oh, that's even better. That chamfer's helped reduce that surface a bit, so it's not completely, there's not too much surface to slow down that wheel. Okay, so now what we need to do is fix this inside here. So the rod should be, we can get rid of that. And if we have a look at the rod, I'm thinking we should have called the rod steward. Yep, little joke there. Alright, so what is the diameter on that? It should be 3 millimeters. Yeah, so we know it's not the rod that's the issue, so it will be the body. Okay, so which one are you? It will be the first one, wouldn't it? Yeah. 2.9. Ooh, that's a bit... Okay, why did I do that? Because I wanted the inside to be tight fitting. Because I wanted the rod to not rotate inside the robot, inside the chassis. Now, is that important? If the axle is rotating, if both wheels can also rotate, then that shouldn't be an issue, should it? Okay, so first of all, make sure that it's 3 millimeters. Now what I did is with the clip, I made that 3.1, did I? Oh, should have left it open. Let's just double check. Because whatever the pressure fit for the clip will be the same for the body, and I'm pretty certain I set that to 3.1 and hope that the printer, yeah, 3.1, and hope that the printer would fix the rest for us. So if we make that 3.1, like so, stop that, save that, and update that, please. And I think that is all that we need to do. I'm not going to be able to do anything else with this anyway today, because I need to cut those rods to size, and I can't really do this in the office, mostly because we've got carpet and sensitive equipment. If this was a proper workshop, then yeah, I'll be in the background cutting it now, but I need to take this outside and do it properly and safely with goggles and all that sort of stuff. Because I don't want to lose my eyesight. I've heard awful stories from friends when they've been working with lathe and finding that they got a bit of metal chipping in the eye. I don't want that to happen to me. These eyes are important. With it, I cannot do this kind of work. Okay, so I think that should be enough. I mean, there's a little bit of clearance between the rod and the body. So I'm hoping, because if you think about it this way, I'm going to print this chassis. If I get rid of that section view, I'm going to print the chassis kind of like that, really. I mean, it doesn't matter which side, but it's going to be from this side upwards or this one downwards, whichever way you want to look at it. And I'm hoping that with this many layers being printed, that there'll be a few imperfections within the layer, and that should provide a little bit of friction in there. What we could do, in fact, we could make the axle, or the hole that the axle goes in, a little bit wider so that it's loose, and then add a couple of bumps inside so that as you push it in, they'll hit it, but then whatever's not being shaved through will provide that friction to keep it in place. So we could do it that way. We can do that with printers. You can't really do that with manufacturing easily. So with traditional plastic molding, traditional plastic molding, you wouldn't be able to do that. Not unless you print the inject both. Well, if you create the chassis into two parts, but then you'll need two individual. You'll need two negative molds for each side rather than just a single one, rather than with a hole in the middle. So with 3D printer, on the other hand, we can add interesting features in the middle of the print, because it really won't make any more difference than no features, so time-wise. Alright, we've got space there, and I'm hoping that we don't put, well, sure, I'm kind of hoping that we won't put the clip in too far in. We'll leave a bit of a slack in there so it's not too tight, and that should allow some motion. It should allow the wheel to rotate freely. I may have to put a cap at the end of the rod with a hole in the middle so the air goes through, and that would provide a guarantee that the clip goes in at the right height every time, and then designing the spacing we need. We could do that, but I don't think that's that important for us, really. Now quickly want to just check that the gaps, yeah, they're both the same. Okay, yeah, and then they both meet in the middle. Okay, so next stream I'll do, which will probably be next week, I will likely either have all these parts already printed for us. There will be a video on YouTube possibly on that. But I'll have this stuff printed, and I'm hoping when I come to test this next week with the proper belt, assuming that the belt is correct and all that, and I've found anything very weird, then we're good to print that, assemble that, and then we can start focusing on the electronics themselves. I know the H-bridge works for this, so I'm happy to use that again. I want to start thinking about what my controller I'm going to be using to drive the whole thing. I am tempted to quickly prototype it using the ball port compatible Arduino. I mean, it's mostly because I got it here. Because I just want to test the motors, make sure they're working, and I can get a RS-232 cable that's thin enough and light enough to power this whole thing. We'll have to have a separate power source because I don't think that the USB cable will do the job. Can you even see that? There we go. So I might do that, then I can quickly use Arduino to test the whole thing, and then once I know the motor and the chassis all work correctly, and the belt is fine, and there's no more mechanical issues that we're going to be dealing with that. Yeah, so if there's no more mechanical issues we have to deal with that, then we'll need to start considering how we're going to mount the electronics, but I don't want to do that until I know what electronics I'm going to be mounting. And again, the electronics have to be simple. I want to be able to do a lot of this stuff without having to rely on anything like a supercomputer or anything like that sort of crazy thing. I mean, supercomputer, that's just, yeah, I mean like a single board computer, not supercomputer. Well, technically speaking, you could say that. Anyway. No, so I don't want to rely on that. I do want to have some wireless in there. So I may actually end up, I do have a couple of Bluetooth modules down here, so I may actually end up using that instead, or the Wi-Fi module which I showed you in the last video. I might do that instead, I don't know. I'm sure that the ESP chips are Arduino compatible. They will be Arduino compatible, so it might use that at a later stage. So I think that's it. So if you like this video, don't forget to subscribe. I am on Twitter. Go over there. You'll get the most update, news of when I'm going to be doing the next live stream. If you've been enjoying this video, don't forget to leave a comment to let me know. And we do have, I mean, I've not really made much of an effort on this, but I do have a Gitter room that people can go to and ask questions when I'm live streaming. So at the moment it's just me, but that's not a big deal. At least I'm getting feedback out of it, so it's not a big problem anyway. So that's it. See you later. Bye.